Lesson 1. Number Sets. In this lesson, we're going to talk about number sets. In mathematical terms, a set is a list or collection of items, and those items can be considered as sets separately as well. So, in this lesson, those items we're going to talk about are numbers. Now, I'm not going to go much into actual set theory, but to give an example, I could have a set containing just the number 2 and have another set containing all even numbers, which would include 2, 4, 6, 8, etc. In this course, though, we're going to be focused on differently defined sets of numbers that we will be using as we move forward. Now, the first set we are going to look at is the set of natural numbers, or counting numbers. These are the numbers that we first learned to count when we were little children. But it goes beyond just counting to 10 on our fingers. The set of natural numbers contain all the numbers that we use to measure real-world data, like height, weight, medicine dosage, distance, etc. Now, there is controversy about whether the number 0 is a natural number or not, but from what we know, it's widely agreed upon that 0 is part of a set of whole numbers, which includes the set of natural numbers as well as the number 0. The next set we are going to look at is the integer set. Building off our previously defined sets, the integer set contains all natural and whole numbers, but now we add all negative numbers. I'm sure you all watching this know what negative numbers are. You write them as the natural numbers, but with a minus sign in front. We'll touch more on negative numbers in a future lesson. Moving on, now we're going to talk about the set of rational numbers. Rational numbers are numbers that can be expressed as a ratio of two integers. The formal definition of a ratio is the relation between two numbers, showing how many times one of them go into the other. So pretty much you can say they are fractions. In contrast, there is a set of irrational numbers. Irrational numbers are numbers that can't be represented as a ratio of two integers. Irrational numbers are more complicated to explain than other ones. And other than square roots, we won't be dealing with them much in this course. But for now, just know that they do exist. Now, we're almost ready to wrap everything up. One aspect of sets as implied in the definition is that a set can belong within another set. Remember an earlier example we gave about 2 being a set by itself, but also being part of another set of all even numbers? That was an example of a single item belonging in a set by itself and in a set with other items. In this scenario, we would say that 2 is in a subset of all even numbers. So with that said, the sets of natural, whole, integers, rational, and irrational numbers are all subsets of the set called real numbers. Real numbers are pretty much any type of number that exists from negative infinity all the way to positive infinity. We spend a lot of time in mathematics dealing with real numbers, so get ready to get used to them. Next, we have the set of imaginary numbers, which is another mathematical concept that we'll explain further in a future course. But what you need to know is any number that has the number I associated with it is an imaginary number. The basic meaning of the number I is that it represents the square root of -1, which doesn't exist in the set of real numbers. To really wrap things up, all of the previous sets of numbers I discussed are considered subsets of the set of complex numbers. Complex numbers are any combination of real and imaginary numbers, usually in the form a plus bi, where a and b are real numbers, and I is the imaginary number. Like we've mentioned before, we're mostly going to be dealing with the set of real numbers in this course, but we will touch on imaginary and complex numbers in a future course. Here's a Venn diagram of the number sets. Each set also has their own symbols, but we'll leave that up to you to research them on your own, as they are not going to be important for this course. And that is it for Lesson 1. See you in the next lesson. Algebra 1, Lesson 2, Integers. We briefly mentioned integers in the previous lesson about number sets, but let's go into them in more depth. We will start by once again defining what an integer is. Integers are the set of whole numbers and their negatives, including 0. Integers can be represented with a number line, where negative numbers are to the left of 0 and positive numbers are to the right of 0. 0 is considered a neutral number. Here is a picture of a standard number line with all the different sets and subsets of numbers pointed out. There are 4 basic operations that we can do with integers: addition, subtraction, multiplication, and division. As you may have learned in earlier math classes, addition and subtraction are inverses of each other, or they are operations that reverse or undo each other. Multiplication and division are inverses as well, but have different properties and special cases that we'll discuss soon. Addition and subtraction of integers are relatively straightforward operations. In your earlier math classes, you were most likely taught to use the number line to add and subtract whole numbers. With integers, we will be incorporating negative numbers with our operations, so we will need to learn how to use them correctly. First, you need to know what the absolute value of an integer is. The absolute value of an integer is the non-negative value of that integer, regardless of its sign. It is specified by 2 vertical bars around the integer. For example, the absolute value of -9 is written like this, which is equal to 9. When adding 2 integers with the same sign, we add their absolute values and attach the sign of the original numbers. For example, 10 plus 5 equals 15, and -11 plus -6 equals -17. When adding 2 integers with different signs, we subtract the smaller absolute value from the larger absolute value and attach the sign of the number with the larger absolute value. For example, 4 plus -8 equals -4, and -3 plus 5 equals 2. Subtraction works in a similar way, with the added step of changing the sign of the second number and then proceeding with addition. For example, 14 minus 12 equals 2, and 14 minus 12 equals 26. Moving on to multiplication and division. When multiplying 2 integers with the same sign, the answer, or what we call the product, is positive. When multiplying 2 integers with different signs, the product is negative. For example, 5 times 6 equals 30, and -5 times -6 equals 30, but -5 times 6 equals -30. Division follows the same rules with the signs as multiplication, but there are some special cases. Dividing 2 integers may give you a fraction a lot of the times instead of a whole number. Fractions have their own special rules when it comes to using the basic operations and applying them correctly to evaluate fractional expressions. We will dive deep into those rules in the next lesson. There are some special cases to consider for dividing with integers. 1. You cannot divide an integer by 0, as it is undefined 2. If you divide a positive integer by a number smaller than itself, you will get a fraction that represents a number between -1 and 0 and 0 and 1, not including 0 itself. 3. If you divide a positive integer by a number larger than itself, and the answer can't be represented as a whole number, then it is an improper fraction. 4. If you divide an integer by itself, the answer is always 1. In conclusion, the understanding of integers is very important, not only for this course, but for higher-level math, science, finance courses, and other similar educational endeavors. Now that we should have a basic understanding of how integers work, let's move on to another important set of numbers mentioned earlier called fractions. See you in the next lesson. Algebra 1, Lesson 3, Fractions. In this lesson, we will take a deep dive into the world of fractions. In a previous lesson, we defined fractions as being represented as a ratio of 2 integers. While that is true, in order to fully understand fractions, we have to define them in a more sophisticated manner. A basic definition of a fraction is that it is a type of number that represents a portion of a whole. One simple cliché example that you have probably seen before is that if you have a pie and cut it up into 6 equal pieces and take one piece out of it for yourself, you have taken 1/6 of the whole pie, with the remaining 5/6 left. Simple enough to understand, right? Fractions are usually expressed in the form of a over b, where a is the numerator and b is the denominator. The numerator represents the number of parts, and the denominator represents the total number of parts. There are 3 types of fractions: proper fractions, improper fractions, and mixed fractions. 1. Proper fractions. A proper fraction is a fraction where the numerator is smaller than the denominator. For example, 2/7, 1/3, and 7/10 are proper fractions. 2. Improper fractions. An improper fraction is a fraction where the numerator is larger than or equal to the denominator. For example, 9/4, 5/3, and 13/6 are improper fractions. 3. Mixed fractions. A mixed fraction is a combination of a whole number and a proper fraction. For example, 3 1/4, 2 2/5, and 3 1/9 are mixed fractions. Now let's get into how we evaluate and solve fraction problems using the basic operations we used with integers in the previous lesson. Adding and subtracting fractions can be done by manipulating one or both of the fractions to have the same denominator. If the denominators are already the same, we simply add or subtract the numerators together and keep the same denominator to get our final solution. Be careful when subtracting fractions, because you may get a negative fraction as the final answer and lose points on a test for forgetting the sign. Here we have a simple example where the denominators are the same. Evaluate 2/9 plus 3/9. We take the following steps to evaluate this expression. 1. We identify that the denominators are the same. 2. We add the two numerators together and place that value as the numerator for our final answer. Remember, we don't have to make any changes to the similar denominators, so our final answer is simply 5/9. Here we have a simple example where the denominators are not the same. Evaluate 6/7 plus 1/2. We take the following steps to evaluate this expression. 1. We identify that the denominators are not the same. 2. We manipulate both of the fractions with multiplication so that the denominators become the same number. We do this by multiplying each fraction by the other fraction's denominator divided by itself. Then we multiply across numerators and denominators. This would be equivalent to multiplying each fraction by 1, which does not change its real value. 3. Now that we have the new manipulated fractions, we add the numerators and keep the new denominator as part of the answer. The math looks like this. 2/2 times 6/7 equals 12/14. 1/2 times 7/7 equals 7/14. Finally, 12/14 plus 7/14 equals 19/14. So our final answer is 19/14. Now, with multiplying and dividing fractions, the rules are simpler. Like in the previous example, when you want to multiply fractions together, you simply multiply across the numerators and denominators to create a new fraction with both a new numerator and a new denominator, unless multiplying by 1 or 0. Here's a quick example. 2/3 times 1/5 equals 2 times 1 over 3 times 5, which equals 2/15. With dividing fractions, you need to switch the numerator and denominator of the second fraction and multiply as usual. Here's a quick example. 5/8 divided by 2/3 equals 5/8 times 3/2, which equals 15/16. Easy, right? It is also important to know how to convert between proper fractions, improper fractions, and mixed fractions. The steps are as follows. To convert an improper fraction to a mixed number, you need to divide the numerator by the denominator and write the quotient as the whole number part. The remainder becomes the numerator of the proper fraction, and the denominator remains the same. For example, to convert 9/2 to a mixed number, you divide 9 by 2 to get 4 with a remainder of 1. So the mixed number equivalent of 9/2 is 4 1/2. Similarly, to convert 4 1/2 to an improper fraction, you multiply the whole number by the denominator of the fraction part and add that value to the numerator while keeping the denominator intact. So 4 times 2 equals 8 and 8 plus 1 equals 9, which brings us back to the improper fraction 9/2. Simplifying fractions is a very important tool to learn to make our work with them much simple, obviously. To simplify a fraction, you need to divide both the numerator and denominator by their greatest common factor, or GCF. For example, to simplify 8 over 16, you need to find the GCF of 8 and 16, which is 8. Then, you can divide both 8 and 16 by 8 to get 1/2. Similarly, to simplify 25 over 30, you need to find the GCF of 25 and 30, which is 5. Then you can divide both 25 and 30 by 5 to get 5/6. In conclusion, fractions are an important part of mathematics, as they help us solve real-world problems that otherwise couldn't have been solved with only whole numbers. They can be added, subtracted, multiplied, and divided using specific rules, as well as converted and simplified to help make evaluating the expressions easier. Keep practicing, and we'll see you in the next lesson. Algebra 1, Lesson 4, Exponents. In this lesson, we will start talking about exponents. An exponential expression is usually stated in the form a to the n, where a is what we call the base. The base is the number that we will be performing the exponential operation on. The number n is the exponent, which tells us how many times we need to multiply the constant with itself, or maybe more intuitively speaking, how many times we need to multiply the constant with the number 1. A basic example of how we would evaluate an exponential expression is with 2 to the power of 2, or 2 squared. This could be evaluated as 2 times 2, or it could be evaluated as 1 times 2 times 2. Both of these methods of evaluation are correct, and the solution equals 4. Here is another example. Evaluate 3 to the power of 3, or 3 cubed. First, we identify the constant, which is also called the base. The base in this expression is 3. Now we look at the exponent, which is the small subscript on the upper right. That number is also 3. What this means is that we multiply the number 3 by itself 3 times. So, 3 times 3 times 3 equals 27. So, 27 is our final answer. We can also evaluate exponential expressions with negative exponents. Like with positive and negative integers, positive and negative exponents also have their own inverse relationship. When we evaluate an integer raised to a positive exponent, we use the integer as our base and multiply it however many times the exponent specifies. However, when there is a negative exponent, you must first change the base integer into its reciprocal and then multiply itself, however many times the exponent tells you to. Here's an example. Evaluate 7 to the minus 2. First, we change the integer 7 into its reciprocal. Since 7 is the same as 7 over 1, we get the reciprocal by flipping the numerator and denominator. So the reciprocal would be 1/7. Then we multiply 1/7 by itself twice, so now we have 1/7 times 1/7, which equals 1 over 49, and that is our correct answer. Other basic rules you need to know about exponents. 1. Watch out for exponential expressions with negative integers as bases. For example, -3 squared is not 9. The negative sign negates the value of +3 squared, which is 9. So, -3 squared is the same as -3 times 3, which equals -9. 2. Any integer raised to the power of 1 is always that integer in most cases. For example, 5 to the first power is still 5. 3. Any integer raised to the power of 0 is always 1. So, whether the integer is 6 to the 0 power, 10 to the 0 power, or even 200 to the 0 power, the solution will always be 1. Finally, any real number raised to an even exponent will always be positive. Any number raised to an odd exponent may be negative. For example, 4 cubed is 64, while -4 cubed is -64. So that's it for the basics of exponents. In future lessons, we will expand on our knowledge of exponents and how they can relate to another type of mathematical expression called the radical. We will also go over some formulas that will be important for you to know to not only do well in this course, but in higher level math and science courses as well. See you in the next lesson. Algebra 1, Lesson 5, Radical Expressions. In this lesson, we'll start talking about radical expressions. Now, at this point in the course, we learned that addition and subtraction undo themselves, just like multiplication and division undo themselves. Like with those operations, we can also undo exponential expressions by taking the roots of them. The most common roots we use in mathematics are the square root and the cube root. Conventionally, we use the square root often enough that we leave out the 2 and just use the radical sign, which implies that the square root of the number inside the radical is being taken. These are examples of what a typical radical expression will look like. This is the main rule for how you would evaluate a simple radical expression. Find the number that, when multiplied by itself, gives you the number inside the radical symbol. For example, evaluate the square root of 16. If you guessed 4, then you would be correct. 4 times 4, or 4 squared, is equal to 16, which is the number inside the radical symbol. Let's look at a second example. Evaluate the cube root of 27. So what this means is, find the number that, when multiplied to 1 3 times, gives you the number inside the radical symbol. If you guessed 3, then you would be correct. 1 times 3 times 3 times 3, or 3 cubed, is equal to 27, which is the number inside the radical symbol. Now, with radical expressions, evaluating them could be as easy as remembering what we call the perfect squares. Perfect squares are radical expressions where we could easily figure out what number multiplied by itself would equal the number inside the radical symbol. The easiest example is the square root of 4. We know that 2 times 2 equals 4, so anytime we come across this radical expression, we don't need to spend too much time guessing that the answer is 2. These are other perfect squares that people usually have no problems with memorization. Like with exponents, radicals also have their own set of rules for operating on them. 1. You cannot take any square root of a negative number and get a real solution. Square roots of negative numbers are in the imaginary and complex number sets, if you remember from the first lesson. 2. Radical expressions that are not perfect squares can still be simplified. This is possible when the number inside of the radical can be split apart into two integers that, when multiplied together, give the same value. If one of those integers under the radical sign is a perfect square, then it can be simplified and multiplied with the other integer under the radical sign that was part of the split. For example, the square root of 8 can be split apart into the square root of 4 and the square root of 2. We know the square root of 4 is 2, so just combine that with the square root of 2 to get our final answer. 2 root 2. 3. Radical expressions cannot be split apart by addition or subtraction. For example, the square root of 7 is not the same as the square root of 3 plus the square root of 4. Finally, look out for negative signs. When the negative sign is outside the radical expression, it can still be evaluated as a real number, but the answer needs to be negated. So, negative root 16 equals negative 4. That is all for the basics of evaluating radical expressions. Like with exponents, we will go over some more advanced operations and come up with important formulas for dealing with evaluating more complex expressions in future lessons. You will need to practice with evaluating these basic expressions, remembering and applying these fundamental rules first. See you in the next lesson. Algebra 1, Lesson 6, Variables. In this lesson, we are going to start talking about variables. This is the part of math where we start to move away from dealing with simple integers, like -2, 3, 5, etc., and start dealing with numbers that are initially unknown. We generally represent unknown values with the letter x. X could be any kind of number from any of the number sets depending on what kind of problem we're solving. So it is not always limited to just real numbers. But in this course, they will be representing real numbers. When we are working on a problem that has more than one or multiple unknown values, we are open to use other letters of the alphabet to represent those values. We could use whatever letters we are comfortable with, but there are conventional letters and symbols that we use to represent certain categories of unknown values. Here is a list of some of the variable naming conventions that are widely used over various branches of math and science. For angle measures, we use the symbols theta, beta, and delta. For exponent, or sums, values we use letters like lowercase k, m, n, and I. For formula values, we use lowercase letters, starting from the beginning of the alphabet like A, B, C, D, and so on. For side measurements for shapes, we use uppercase letters starting from the beginning of the alphabet. For time and velocity values, we use lowercase t and v. And for coordinate points, we use x, y, and z. Variables can be used to create formulas that make it easy to solve expressions that involve integers. Like stated previously, we usually use the letter x to describe an unknown value, but in algebra, we usually use the letters A, B, C, and D to create formulas. In a previous lesson, we talked about fractions, but with variables representing any of the numbers in an expression, we could just follow the formula to come up with an answer for the problem. For example, the following formula is one you could use to add fractions with different denominators. A over B plus C over D equals A times D plus B times C all over B times D. Instead of using the more traditional methods, using this formula makes it even simpler to evaluate the expressions, because you can just plug in the different variables into the output, do some multiplication and simplification, then arrive at the correct answer. We can also do simple operations with variables, the same way we can do it with integers. If x is an unknown number, and I want to add the same amount x to it, then I would end up with 2x. It's the same idea as having one orange, then receiving another one orange, and ending up with 2 oranges. This obviously applies with subtraction as well. What if we want to add or subtract different amounts? If I have x amount of something and I want to give away a w amount of it, then the variable expression that represents this is x minus w. We know these two amounts are unknown, but we know their value is different, so it's required that we use different variables to represent each amount. We could combine or find the difference between various multiples of the same variable. Let's say I pick 5 grapes from a branch, and then 5 minutes later, I pick 3 more grapes. Well, now I would have 8 grapes. The same logic applies with variables. If I have 4x, and I add 6x to it, then I would have 10x. This is called combining like terms. This can only work when you are combining terms with the same unknown variable. The coefficient, which is the number attached to the front of the unknown variable, could be the same or different. As long as you follow the basic rules of operating with integers, then you can easily evaluate expressions with like terms. Variables are going to be a very important part in mathematics, from algebra to much more advanced subjects, so it is a good idea to get practice with using them. In this course, the main variables we will be using are x and y, and we will explain what their properties are in a future lesson. See you in the next lesson. Algebra 1, Lesson 7, Laws of Exponents. Remember your practice with variables in the last lesson? That experience will come to use when evaluating different exponential expressions, because we're going to use formulas or laws to evaluate them. The first law we'll call the product law. It says that if two exponential expressions have the same base a, when you multiply them together, you add the exponents and keep the base the same to get the answer. Evaluate 5 squared times 5 cubed. First, we identify that the base of both expressions are the same. The base is 5, so it will also be the base in our answer. Then we look at the exponents associated with the base and add them together. So 2 plus 3 equals 5. So our final answer is 5 to the 5th power. The second law we'll call the quotient law. It says that if two exponential expressions have the same base a, when you divide them, you subtract the exponents and keep the base the same to get the answer. You start with the exponent in the numerator, and then subtract the exponent in the denominator from it. Evaluate 7 to the 8th power over 7 to the 5th power. First, we identify that the base of both expressions are the same. The base is 7, so it will also be the base in our answer. Then we look at the exponents associated with the base and subtract the lower exponent from the higher exponent. So 8 minus 5 equals 3. So our final answer is 7 cubed. The third law we'll call the power law. It says that if you raise an exponential expression to another exponent, then the answer is the base raised to the two exponents multiplied together. Evaluate 9 cubed raised to the 4th power. First, we identify our exponential expression. Usually it will be inside a pair of parentheses. The expression is 9 cubed. Then we identify the exponent it is being raised to, which is usually outside the parenthesis to the upper right. Lastly, we multiply the exponent from the expression inside the parenthesis to the exponent from outside the parenthesis. So 3 times 4 equals 12. We keep the same base of 9 according to our formula, and we get a final answer of 9 to the 12th power. Finally, we have the power of a quotient law. It says that if you raise a quotient a over b to the nth power, you can apply the power to both the numerator and the denominator. For example, 2/5 squared is equal to 2 squared over 5 squared. When you evaluate the numerator and denominator, you get 4 over 25 as the final solution. There are a few more formulas we need to know when dealing with exponents, but those formulas are related to the laws of radical expressions, which we will cover in the next lesson. Make sure to get some practice with these laws first, and we'll see you in the next lesson. Algebra 1, Lesson 8, Laws of Radical Expressions. Just like with exponents, we have formulas or laws that help us navigate through operating with radical expressions. It is important to know how exponents and radicals are related to each other. Radical expressions could also be written as exponential expressions by using fractional or rational exponents. Take a look at the formulas below, and we'll do a quick example next. Convert the following radical expression to an exponential expression. We have the 5th root of x. Referring to our formula, we can rewrite this as x to the 1/5 power. Convert the following radical expression to an exponential expression. We have the cube root of x squared. Referring to our formula, we can rewrite it as x to the 2/3 power. In our previous lesson on radical expressions, we discussed how we can split apart certain radical expressions that are not perfect squares. For example, we could split the cube root of 54 up like this. We look at the 54 inside the radical and recognize that we could split it up into 27 times 2. Doing that, we recognize that 27 is 3 cubed, so the cube root of 27 would be 3. So after the split up, we have the cube root of 27 times the cube root of 2. We simplify the cube root of 27 to be 3, and we just multiply by the remaining cube root of 2. So our final answer is 3 cube root of 2. Some numbers will be trickier to factor, but with enough practice you should be able to recognize these opportunities for simplification. In any case, you can use this formula to assist you. When we convert our radical expressions into fractional exponents, we could create new formulas that are based on the previous formulas we learned about when we reviewed the laws of exponents. For example, the square root of 24 could be rewritten as 24 to the 1/2 power. The 24 can then be split up into 2 factors, 6 and 4. And finally, the 1/2 exponent could be distributed to both the factors. This gives us the following formula. Like with exponents, a radical sign could be distributed to both the numerator and denominator of a rational expression. A rational expression is just a fancy way of saying a fraction. So the square root of a over b is equal to the square root of a over the square root of b. The same rule would apply if we were raising it to an integer power, as well as if we rewrote the square root to be the 1/2 power applied to both the numerator and the denominator. Another formula that shows this is below. Like with variables, you can add and subtract like radicals, meaning radicals with the same root and same radicand, the number inside the radical symbol. For example, we can add 5 root 3 and 7 root 3 because they have the same number inside the radical symbol, and they are both square roots. So, when we combine them by addition, we get 12 root 3. We would not be able to add or subtract radical expressions like 4 cube root 2 and 6 root 5, because their roots and radicands don't match up. Lastly, to make fractions that contain radical expressions in the denominator easier to work with, we could multiply both the numerator and denominator by that radical expression, so it's like we're multiplying by 1. This will put the radical expression in only the numerator without changing the value of the original expression. For example, we have the radical expression 7 over root 8, and we want to rewrite it by rationalizing the denominator. First, we use the root 8 in the denominator and multiply it with both the numerator and denominator of the original expression. Then we do the simple multiplication to get our final answer, which is 7 root 8 over 8. Remember, we are still using our laws of exponents when we multiply root 8 by itself. We rewrite root 8 as 8 to the 1/2 and square the whole term, which means to evaluate it, we have to multiply the inside and outside exponents together. This gives us 8 to the first power, which is equal to 8. So now we are equipped with some new formulas for operating with and simplifying radical expressions. It is important to know the correlation between radical expressions and their exponential forms, so that you can decide which formulas you are comfortable working with. If working with exponents is easier for you, you are now equipped with the tools you need to convert radical expressions into exponential ones and vice versa. See you in the next lesson. Algebra 1, Lesson 9, Order of Operations. The order of operations is a set of rules and conventions used to determine the order in which mathematical operations should be performed. This is crucial because the order of which you do these operations will affect how accurate your results are. A standard mnemonic we use for the order of operations is PEMDAS. PEMDAS is an acronym that stands for parentheses, exponents, multiplication and division, and addition and subtraction. We need to apply each of these operations, from left to right, in that order, when it is necessary to do so. Let's do an easy example. Evaluate 5 divided by 5 plus 2 first. We start from the left and point out that we have a division problem that leads into an addition problem. Since the letter D for division comes before the letter A for addition in the PEMDAS mnemonic, we perform the division operation first, then perform the addition operation after that. So we compute that 5 divided by 5 equals 1, and then 1 plus 2 equals 3, so our final answer is 3. For this example, let's kick it up a notch. Evaluate 3 squared times 2 minus 6. First, we identify that 3 squared is inside a pair of parentheses. P comes first in PEMDAS, so we evaluate anything that is within the parentheses first. 3 squared is equal to 9. Next, we see a multiplication problem and a subtraction problem. Since M comes before S in PEMDAS, we multiply 9 by 2 and then subtract 6. So altogether we have 9 times 2 minus 6, which equals 12. In the last two examples, we had the operations laid out in order already, so even if you just went from left to right, you would have reached the right answer. But the purpose of PEMDAS is to help you evaluate expressions that are written in any random order. Let's work on this next example. Evaluate 5 plus 7 minus 2 cubed times 3. First, we look for anything that is surrounded by parentheses, since P is the first letter in PEMDAS. 7 minus 2 cubed is inside a pair of parentheses, so we evaluate that first. We now have a PEMDAS problem inside another PEMDAS problem, sort of like PEMDAS inception. No need to overcomplicate things, though we just stick to the same rules. E, which stands for exponents, come before S, which stands for subtraction. So we evaluate 2 cubed to be 8, and then subtract from 7 to get minus 1. Now we have minus 1 in the parentheses, and can move on with the rest of the original problem. Now we have our problem written as 5 plus minus 1 times 3. At this point, it is intuitive to just simplify 5 plus minus 1 to 4, and then multiply by 3, but that is not really going in the right order. To go in the right order, you start by using the multiplication operator first, then doing any addition and subtraction. So, we have 3 times minus 1 plus 5. 3 times minus 1 equals minus 3, and minus 3 plus 5 equals 2, which is our final answer. There is a somewhat hidden step that you need to know about when it comes to the order of operations. We say that it is hidden because in some cases it could be the first step, it could be done in the middle, or it could be a last step. That step is called using the distributive property. The distributive property allows us to simplify expressions by distributing an integer across a sum or difference of terms. This can help us to make complicated expressions simpler and easier to work with. For example, we have the expression 3 times 4 plus 5 written like this with the 4 plus 5 inside the parentheses and the 3 attached to the front. We can rewrite this expression by multiplying or distributing the 3 to the 4 and 5 inside the parenthesis and then evaluating the resulting terms. This is how we would work it out and get the final answer of 27. The distributive property will be an important tool to use once we get to more advanced algebra areas. When it comes to PEMDAS, it is important to know that it is easier to make distributing an integer the last step to take after you have used PEMDAS rules to evaluate all the expressions inside the parentheses to come up with a single number or term. Let's look at one more example. 6 times 10 divided by 2 minus 5 squared. First, we use our traditional PEMDAS rules to evaluate the expression inside the parentheses. In this case, we get minus 20. With only minus 20 in the parentheses, we simply multiply it by the 6 attached to the parentheses to get minus 120. Note, we could have rewrote minus 20 as minus 10 and applied the distributive property with the number 6 and arrived at the same answer. Using the distributive property in this way is how you will continue to use it in later mathematics courses. This concludes this lesson and Unit 1. It is important that you use any other practice materials available to you to make your understanding of these beginner algebra topics concrete. In the next unit, we will be moving on to solving different types of equations. See you there. Algebra 1, Lesson 10, Solving Basic Equations. Now let's get into the good stuff. In this lesson, we're going to start exploring equations. An equation is a mathematical statement that states that two expressions or values are equal to each other. For example, in a previous lesson, we mentioned that fractions can also be division problems. The fraction 12 over 4 is the same as 12 divided by 4. So we can write the fraction in an equivalent statement, defining it as being equal to the value of the division expression. We can write it as 12 over 4 equals 12 divided by 4. We can write equivalent statements like the previous one with any expression or value, if we know that they both have the same value on either side of the equation. For example, the square root of 4 equals 2, or 2 squared equals 4. The most important element of an equation that you must remember is that in the process of solving an equation, any operation you do on the left side of the equation must also be done on the right side, and vice versa, Otherwise, the mathematical statement will not be equal. Let's look at an example. Here we have an equation. The square root of 9 equals 3. If we add 2 to the square root of 9, we must also add 2 to 3 in order for the statement to be true. So, the square root of 9 plus 2 equals 3 plus 2. You could evaluate the right side of the equation, and it will be true because the value is equal to the left side of the equation. So we can rewrite this as the square root of 9 plus 2 equals 5. The same concept could be applied to subtraction as well. What a surprise. 2 cubed equals 8. 2 cubed minus 3 equals 8 minus 3. So 2 cubed minus 3 equals 5. Now let's use this concept with variables. Take a shot at this. If 5 plus 3 equals x, what does x equal? If we evaluate 5 plus 3, then we'll get 8, which by definition must be the same value as the number on the right side of the equal sign. So x equals 8. Let's take it a step further. 7 plus x equals 2. When we start doing these kinds of problems, it's always best to try to get x by itself on whatever side of the equation it is on. So, to get x by itself, you need to subtract 7 from the left side. But according to the math gods, you have to also subtract 7 from the right side. So now we get this. 7 plus x equals 2. Subtract 7 from both sides. Now we have x equals 2 minus 7, which equals minus 5. You probably saw this coming, but just like how we can use the plus and minus operators to help us solve equations, we could use multiplication and division to manipulate equations to solve for an unknown variable. Let's get right into our first example. Example 1. Solve the following equation for x. 7x equals 77. Like with all equations, we want to make sure we end up with two results at the end. We want both sides of the equation to be of equal value. We want one side of the equation to be just the variable by itself. So how can we manipulate this equation to get both results? Well, the way this equation is set up, we can see that in order to get the variable by itself on the left side, we would have to divide by 7, so that it cancels out with the 7 on the top, and makes us have x by itself. And to make sure we follow the other important rule, we also have to divide the right side of the equation by 7, to make sure that both values are equal. So when we divide 7x by 7, we get x, and when we divide 77 by 7, we get 11. So our final result is x equals 11. Now you may have noticed that we started off with a division example instead of multiplication. It's because using multiplication to solve equations often involves working with fractions, and we all know how that makes a lot of people cringe. But if you know how to work with fractions, it won't be difficult to work those types of problems out. Let's look at an example. Example 2. Solve the following equation for x. 1/3 x equals 8. Now, one important rule to know when trying to use multiplication to solve these equations is the reciprocal rule. We use this rule to divide fractions by other fractions, but also use it to simplify equations with fractions as constants. So, we multiply 1/3 by 3 over 1, which if we use the multiplication operation rule we learned in a previous lesson, we would get 3/3, which simplifies to 1 over 1, which is just 1. Remember, the x was still attached to the 1/3, which we got rid of by multiplying by the reciprocal. Getting rid of in math terms mean that we turned it into the number 1. So now we have 1 times x, which is just x on the left side of the equation. What do we do next? Is that a broken record I hear? Yes, we have to multiply the right side by that same reciprocal. Now remember, the reciprocal, 3 over 1, is the same as 3, so we basically have to multiply both sides by 3 to get the final answer. 8 times 3 equals 24, so the final answer is x equals 24. If you are trying to solve for an unknown value multiplied by a fraction, another simple rule to use is to multiply both sides of the equation by the denominator of that fraction. So in the last example, We could have just solved it by looking at the denominator 3 in the fraction and multiplying both sides of the equation by that number to get x equals 24 at the end. Use whatever rule you feel comfortable with. Now, for the final challenge. All of our previous examples involved solving equations with 1 or 2 steps, but the reality is, you're going to need to solve equations using multiple steps as you advance further in math and science. The same rules still apply, but you will need to keep track of all your operations so that you follow the fundamental rule that an equation must always have equal value on both sides. Pause and solve the following equation. We will work it out on the next part. Final example. We have 2x plus 5 equals 7x plus 8. A good first step is to always try use basic operations to get the unknown variable on one side and the constant on the other. It is a personal habit of mine to start with the constants, but you can start however you want as long as you get x equals something at the end. So, I start off by subtracting 5 from the left side because I'm comfortable working left to right, and I can get the 2x by itself, which makes life easier. Since I chose to subtract 5 from the left side, I have to subtract 5 from the right side as well. So now we have 2x equals 7x plus 8 minus 5. Remember when we talked about variables and like terms? Constants are considered like terms, so we can combine them anytime we can to make our work easier. So we get 2x equals 7x plus 3. We still want to get an x equals something. So in order to do that, we have to subtract 7x from both sides to end up with minus 5x equals 3. Divide both sides by minus 5, and our final answer is x equals minus 3/5. In your academic career, you'll run into different types of equations that may be more complex than the ones in the previous examples, but the rules you use to solve them still remain the same. Just make sure both sides of the equation are equal, and make sure you get the unknown value by itself on either side. Mostly by convention, the unknown value will be on the left, but it doesn't always have to be the case. Hope we didn't lose you yet, because we aren't even halfway done yet. See you in the next lesson. Algebra 1, Lesson 11, Solving Equations with Roots and Exponents. I know you all probably saw this coming. There are always patterns in math. Nothing is really all that unpredictable. We talked about operations with expressions, variables, and so far, we talked about most of those operations with solving equations. So it's easy to deduce that we could use the rules of exponents and radicals to solve certain equations as well. Let's start off with a simple example. Example 1. 2x equals the square root of 16. Note that you could rewrite the square root of 16 as 4. Now the equation would look like 2x equals 4, and you could simply divide both sides of the equation by 2 to solve for x, which equals 2. We also need to be reminded of the inverse relationship between exponents and roots to help us solve equations, just like we use the inverse relationship between multiplication and division. We can combine the rules we learned from previous lessons to manipulate equations so that we can isolate and solve for the unknown variable. Let's say we are trying to solve the square root of x equals 6. We can solve this intuitively by already knowing that the square root of 36 is 6. But a lot of the equations we will be solving will require more work, especially when we add more operations to them. Example 2. The square root of x plus 1 equals 17. In this example, it is not too intuitive what x could be, so we must do some more work. If we remember, exponents and roots in most cases undo each other. The square root of x raised to the second power is just x. The cube root of x raised to the third power is also x. You can already start to see a pattern. So, to solve an equation with a square root of an unknown, we need to isolate it on one side and then raise it to the second power or square it, so that we end up with just x. We also have to, as always, keep track of our operations on the side of the unknown variable, and apply them to the other side of the equal sign as well. Going back to our example, we can see that we need to get the square root of x by itself on one side to make life easier. We need to get rid of that one by subtracting it on both sides. So now we have the square root of x equals 16. To solve for x, we need to raise the square root of x to the second power or square it. Remembering we must also raise 16 to the second power, we end up with our final answer. X equals 256. We can also use the inverse rule to solve equations with exponents. For example, x cubed equals 64. In this example, we can simply take the cube root of both sides to get the x by itself on one side and balance the equation on the other side. So we end up with the cube root of x cubed equals the cube root of 64. The cube root of 64 happens to be 4, so our final answer is x equals 4. Let's take all our previous knowledge and solve this challenge problem. Note: it is important to know basic arithmetic when solving these types of equations, because trying to figure out what 9 cubed is may require some extra work if you don't have a calculator. Final example: solve the following equation. The cube root of x plus 1 equals 9. You will notice in this example that we are adding 1 to the unknown variable. In this scenario, we must remember our basic radical rules and not split them apart, but to treat them as one expression. So when we raise the entire left side of the equation to the third power, we are left with just the term x plus 1. But wait, that means we need to have 9 cubed on the right side. Does that sound familiar? If you punked out and got a calculator, you'll find out 9 cubed is 729, but we still need to get the x on the left side by itself, so we subtract 1 on both sides. That means our final answer is 728. It is important that you get practice with operating on exponents and radicals, and know the rules of them like the back of your hand. Knowing them, as well as the basics of solving equations, will help you get through the knowledge checks and future quizzes and exams. Now to move on to another class of equations in the next lesson. See you there. Algebra 1, Lesson 12, Solving Equations with Absolute Value. Now let's start solving equations that involve an interesting operation called the absolute value. We like to define the absolute value of a number like this. The absolute value of a number defines its distance from 0 on the number line. The absolute value of a number is never negative. Those are basically the main rules you need to know when solving equations with absolute value. For example, the absolute value of the number -6 can be expressed as follows, with the number -6 between two vertical bars. The absolute value of -6, and then we would evaluate that expression to equal the number 6 like this. The absolute value of -6 equals 6. We can use our knowledge of solving multi-step equations and apply it to solving equations with absolute values. Example 1. The absolute value of x minus 3 equals 15. For this equation, we need to identify the expression between the absolute value bars and realize that the equation is asking us to find two solutions. X minus 3 equals 15, and x minus 3 equals -15. These two equations could be solved by one step each, so we end up with our two solutions. X equals 18 and x equals -12. Example 2. 5 times the absolute value of x equals 35. With this example, we simply isolate the absolute value containing the unknown variable by dividing both sides of the equation by 5. We end up with the absolute value of x equals 7, which means that x could be 7 or minus 7. One thing to note is that because of the nature of absolute value equations, sometimes you will have no solution. One basic example is the absolute value of x equals minus 3. Based on the definition of an absolute value, it is impossible for it to be evaluated to be a negative number. So in those cases, we will simply write no solution. Now that you know the basics, let's do a challenge problem. Solve the following equation. 2 times the absolute value of x plus 6 plus 5 equals 3. Before we solve, let's ask ourselves these 3 questions. Does this equation have 2 solutions? Does this equation have 1 solution? Does this equation have no solution? Let's dive right in and find out. We will first start by trying to isolate the expression that is contained within the absolute value. We need to do 2 steps to make it happen. We subtract 5 from both sides. We divide both sides by 2. After doing those steps, we end up with the absolute value of x plus 6 equals minus 1. Our first instinct would be trying to break up the absolute value and try to solve 2 equations. But if you take a closer look, you will realize that the equation is asking for the absolute value to equal a negative number, which, as we should already know, is impossible. So our final answer is no solution. Solving absolute value equations will vary in difficulty, and the amount of work you need to do to solve them. But if you have already practiced solving regular algebraic equations, absolute value is just another tool in your arsenal to help solve more difficult equations. See you in the next lesson. Next. Algebra 1. Lesson 13. Evaluating algebraic expressions. So far, we've looked at variables as unknown values that we could use operations on. But now let's try to evaluate these expressions we looked at with defining the values of the variables. Example 1. Evaluate 3x plus 2 when x equals 3. Since we are given what the unknown variable is equal to, therefore it is known now, we plug in that value in place of the variable and evaluate the expression. So if x equals 3, we can write the expression like this: 3 times 3 plus 2. And now we evaluate it. 3 times 3 equals 9. 9 plus 2 equals 11. So when we evaluate the algebraic expression, given the value of the variable, we get 11. One important fact to know is that you can have 2 different variables in an algebraic expression. Usually these 2 variables will have 2 different values. Let's look at this next example where we use z to represent another variable that we need to evaluate with the information given. Example 2. Evaluate 5x plus 2z when x equals 4 and z equals 2. Like with the previous example where we were given the value of x, we simply replace x in the expression with its given value. We do the same with the variable z. So now we have 5 times 4 plus 2 times 2. When we evaluate this expression, we get 20 plus 4, which is equal to 24. We could also evaluate expressions involving exponents and radicals. We still apply the same rules we've learned about exponential and radical expressions, and evaluate the expression with the given values for the variables. Example 3. X squared plus 3x when x equals 1. Once again, we have to plug in the known value into the variable. This time we have to evaluate it as an exponent. So now we have 1 squared plus 3 times 1, which when evaluated equals 4. Let's do one final challenge problem. Pause and do this one on your own, and we'll reveal the answer on the next part. Evaluate the following algebraic expression. X cubed minus 5z all over y, when x equals 2, z equals 4, and y equals 0. If you remember your basic rules about fractions, you would have quickly realized that you were dividing by 0, which is a big no-no, and will have the math gods banish you into purgatory. It is important to know that when you come across problems like this on an exam, you have to state that the answer is undefined. We can confirm the numerator to see if you at least did those steps right. 2 cubed minus 5 times 4 equals minus 12. So our final undefined answer would be minus 12 over 0. Evaluating algebraic expressions when we are given the values is all about matching the variable with the value it is equal to and using basic arithmetic to come up with a final answer. This is a very important skill to practice, and you'll get a little bit of it in the knowledge checks. See you in the next lesson. Algebra 1, Lesson 14, Algebraic Word Problems. There are going to come times when you take any math or science course that you are expected to take your knowledge about how to solve equations and use them to help you solve certain types of word problems. I know, doing word problems could be a challenging task, but it is necessary to be able to get through them so that you know that your understanding of how to work with equations is solid. Here's a couple of tips for solving word problems that require you to set up and use equations. 1. Extract the numerical information. Even though they are word problems, they contain numerical values that you need to use to set up the proper equations. It is important to set that information aside so you know what the known values are. 2. Locate the relevant variables. If the word problem states a quantity that is unknown, then most of the time that is a variable that you need to make sure is represented in the equation. 3. Set up the equation by translating the language in the word problem to a mathematical language. Make sure that when you're setting up the equation that you're on top of your reading comprehension. If I say, I have 5 apples and 2 oranges, how many fruits do I have? You will have to comprehend the fact that both apples and oranges are fruits, which means in this example they are like terms, so you would add the 5 and 2 together and conclude that I have 7 fruits. The word problems we are going to work on will be more complicated than that last quick example. But if you identify the numerical values and unknown numerical values, all you need is a little logic and reading comprehension to set up the right equations and use the tools you learned in the previous lessons to solve them. Example 1. Jerry is 6 years younger than 5 times the age of Tom. If Tom is 10, how old is Jerry? This is a typical age word problem. The main idea is to try to translate the word problem into an algebraic equation and then solve it how we usually solve equations. This is one of the easier ones because we only need to find Jerry's age and already know Tom's age. We can write Tom's age as t and Jerry's age as j, then write the following equation. J equals 5, t minus 6. Since we know t is 10, we simply plug it in and evaluate the expression. So, j equals 44, meaning that Jerry is 44 years old. Problems like these can be confirmed by using simple logic, but it is important to build the foundations here for more difficult word problems. Example 2. Simon is 14 years older than Ned. In 8 years, he'll be twice as old as Ned is now. How old is Simon now? This problem is going to take a little bit more setup, but the basics should still apply. First, let's define Simon's age as S and Ned's age as N. So let's write our first equation. S equals n plus 14. This equation shows that Simon is Ned's age plus another 14 years. Our next equation is the equation for Simon's age, 8 years in the future. S plus 8 equals 2n. So now we have our present age equation and our future age equation for Simon. If we isolate the s on the future age equation, we'll get s equals 2n minus 8. Now we can make a third equation with only one unknown variable, n. N plus 14 equals 2n minus 8. Subtracting 2n from both sides and subtracting 14 from both sides to isolate the n variable, we have minus n equals minus 8 minus 14, which simplifies to minus n equals minus 22. Finally, dividing both sides by minus 1 will give us n equals 22. So, Ned is 22 years old in the present time. The problem asked us to find Simon's present age, so we go back to that equation and plug in 22, and we get that Simon is 36 years old. Final example. Yes, this is not over yet. Use the previous equations in the last example to find out Simon and Ned's ages, 8 years in the future. Pause the video to work on the problem, and the answers will be on the next part. So, to answer that last question, we simply add 8 to their present ages. You will notice that Simon's future age is 44, which is twice Ned's current age of 22. So, it looks like we did the problem correctly. Always go back and make sure that your answers logically make sense in these types of word problems. If you find yourself getting negative ages for answers, then you know you messed up and need to go back and fix some things. Problems like these will have varying levels of difficulty and setup, but once you get enough practice, you will begin to build more confidence when doing them. See you in the next lesson. Algebra 1, Lesson 15, the coordinate plane. One of the most crucial concepts that you will need to learn about in mathematics, and not just in algebra, is the XY coordinate plane and the Cartesian coordinate system. I'll leave it up to you to research who Cartesian is. In math and science, and all the subjects that fall under that umbrella, we use the 2D coordinate system to help us understand various pieces of data and how they relate to each other. What is not usually stated is how important the system is when it comes to learning more advanced mathematical concepts that are taught in calculus. If you can understand and master the ins and outs of this system, then a lot of what you will learn in later math courses will be much easier to digest. For now, let's just start with the basics. This is a graph of the typical 2D XY coordinate plane. As you can see, we have a horizontal number line that we call the x-axis. It intersects with a vertical number line, which we call the y-axis. The point at which these two number lines cross is called the origin. We can mark points on this plane called coordinates. Coordinate points are written in the form x, y, where the x-coordinate represents a point on the x-axis, and the y-coordinate represents a point on the y-axis. The point shows up on the plane, assigned to those 2 points at the same time, like in the example below. The coordinate plane could also be divided into 4 quadrants as shown below. They are conventionally written as Roman numerals and go from 1 to 4 counterclockwise on the plane. The quadrants give you more specific locations of where certain points will be, based on whether they are negative, positive, or any combination of both. For example, find which quadrant the coordinate point, 5 minus 3, is in. Pause and try to do the example. The answer will be on the next part. If you picked quadrant 4, you would be correct. In fact, all coordinate points with a positive x-coordinate and a negative y-coordinate are in quadrant 4. Here are the other combinations of coordinates and their respective quadrants. Coordinate points can also be used to figure out the distance between two or more points on a flat surface. For example, look at the graph here and describe the distance from point A to point B using units up, down, left, or right. If you said point B is 4 units to the right and 2 units down from point A, you would be correct. You can also say point A is 2 units up and 4 units to the left of point B. There are formulas for more complicated distance problems, like when we start dealing with the distances of lines drawn between points, but we'll save that discussion for a later time. Here is a challenge problem. Coordinates can be used to plot data about the relationship between two or more variables. Let's say the x-coordinate represents the number of minutes that Timmy has to walk up a hill, and the y-coordinate represents how many sweat droplets come out of his skin pores per minute. We plot all the points of data on the coordinate plane like this below. How many droplets of sweat has come out of Timmy's skin pores when he is 3 minutes up the hill? If you chose 6 drops of sweat, then you are correct. Coordinate points can be used to analyze more meaningful relations between two or more sets of data. It also has other real-world applications, such as navigation, computer graphics, architecture, etc. So, as usual, it is important to understand the basics. See you in the next lesson. Algebra 1, Lesson 16, Slope of a Line. In the last lesson, we discussed the coordinate plane and how we can use coordinate points to mark locations using the x and y coordinates. We also learned how we could plot different coordinate points and analyze the distance between them. In this lesson, we will learn how to measure a rate of change between 2 points by drawing a line through them and calculating the slope. The slope of a line is a measure of how steep the line is. It is also defined as the ratio of the change in the y-coordinates to the change in the x-coordinates between any 2 points on the line. If we define the coordinates of 2 points on the line as x1, y1 and x2, y2, then the slope of the line, denoted as m, can be calculated using the following formula: m equals y2 minus y1 over x2 minus x1. The slope can be positive, negative, 0, or undefined, depending on the direction and steepness of the line. A positive slope indicates that the line is moving up and to the right, while a negative slope indicates that the line is moving down and to the right. A slope of 0 indicates a horizontal line, while an undefined slope indicates a vertical line. Let's calculate the slope of a line between 2 coordinate points. Draw it on the coordinate plane and analyze the steepness of the slope. Example 1. What is the slope of the line between points 1, 4 and 3, 2? To solve this problem, we refer to the slope formula and plug in all the points where they need to be. Let's take a look at the formula again. So, if we plug in the numbers correctly, we will get 2 minus 4 over 3 minus 1. Evaluate and we will get minus 2 over 2, which equals minus 1. Looking at a graph of the line going through both points, and knowing that the slope is negative, we can see that the graph has the right orientation of the steepness of the slope. Example 2. What is the slope of the line between points 3, minus 5, and minus 6, minus 5? Like with the previous examples, we plug in the coordinate points into the slope formula. We get minus 5 minus minus 5 over minus 6 minus 3, which equals 0 over minus 9. This gives a slope of 0, meaning that the line is flat and not steep. We'll show you the graph in the next part. As you can see, the horizontal line goes through point minus 5 in the y-axis. This means that the distance between any 2 points on the line will have the same slope of 0. Example 3. What is the slope of the line between points minus 7, 8, and minus 7, 14? Let's chug through this one like we did the last 2 examples. We plug in the coordinate points into the slope formula. We get 14 minus 8 over minus 7 minus minus 7, which equals 6 over 0. Houston, we have a problem. The math gods have been alerted because you probably thought you could divide by 0. Foolish mortal. This gives an undefined slope, which will be shown on the upcoming graph. This graph shows a vertical line going through the x-axis. This line is infinitely steep, so its slope is undefined. This happens when we calculate the slope formula and end up with a 0 difference between the 2 x-coordinates in the denominator. Why don't we say that the slope is infinity instead of saying it's undefined? Well, go take that up with the math gods and get struck by lightning if you want to. That's just how it is. Higher-level math courses will go deeper into the distinctions, but for now, let's just say the slope is undefined and not phi. That's our lesson on the slope of a line. The slope formula will become important in our next few lessons, so it's a good idea to get some practice using it. Recognize the orientations of positive, negative, 0, and undefined slopes on a coordinate plane as well. See you in the next lesson. Algebra 1, Lesson 17, Slope-Intercept Form. In the next few lessons, we are going to be discussing and learning about linear equations. Linear equations are simply equations that are used to represent lines that are on the coordinate plane. In the previous lesson, we discussed slopes of lines going through points on the plane. Those same lines could also be defined by equations as well. Here we have a graph of a line going through the origin with a positive slope. This line has a corresponding equation of y equals x or x equals y. This means that every point on the x-axis equals the same point on the y-axis. Equations are always more flexible than that, though. Here we have the linear equation y equals 2x, which means that for every value of x, the y value is twice that. So, you would be drawing a line through coordinate points that are equivalent to what the equation states. For example, you would be drawing a line through points 1, 2, 2, 4, 3, 6, etc. Let's do another example to help us really understand how linear equations work. Example 1. We have a linear equation y equals 3x minus 1. How would that be represented on a graph? Well, we can start by looking at the equation and figuring out coordinate points based on what the equivalent statement is. So, what the linear equation is saying is that for every point on the x-axis, the y-axis will be 3 times that point and will be subtracted by 1. If we pick the point 5 on the x-axis, then the corresponding point on the y-axis will be 5 times 3, which equals 15, minus 1, which equals 14. So, a point that the line will go through is point 5, 14. We represent linear equations in different forms. Each form serves their own purpose in what type of information they can reveal, but they can all be manipulated to look like the other forms through some of the algebra work we learned in previous lessons. In this lesson, we will look at the properties of the slope-intercept form of a linear equation. A linear equation in slope-intercept form will almost always have this format: y equals mx plus b, where y is the value of the point on the y-axis. M is the slope of the line, as discussed in the previous lesson. X is the value of the point on the x-axis. B is the single point on the y-axis the line intersects with, also called the y-intercept. Let's look at the previous linear equation and dissect it. Y equals 3x minus 1. Y is the value of any point corresponding to the y-axis, once the other side of the equation is evaluated. M is the slope of the line that can also be calculated with the slope formula, using any coordinate 2 points you can derive from the equation. X is the value of any point corresponding to the x-axis. Usually you pick random values of x to find the corresponding values of y to plot points on the plane to draw a line through. B is the value that shifts the intersection of the line through any point on the y-axis, based on the operator in front of it. Let's do an example with a different equation and see if you can find all the components. Example 2. Find the y-intercept and slope of the linear equation. Y equals minus 5x plus 4. By just following the slope-intercept form of a linear equation, we can see that the slope of the line the equation represents is minus 5, and that the y-intercept or b is 4. Like there is a y-intercept, there is also an x-intercept for linear equations. The basic rule is that to find a y-intercept, you plug in 0 for x and evaluate the equation. Knowing that the slope multiplied by 0 will always be 0, y will always equal the y-intercept. Likewise, to find the x-intercept, you will have to plug in 0 for y and solve for x. The slope-intercept form is set up so that it is easier to find the y-intercept, but to find the x-intercept, you will need to do a little more work. Example 3. Find the x-intercept for the following equation. Y equals 6x minus 5. When finding the x-intercept, we need to find the single point the line goes through on the x-axis. We can do that by replacing y with 0 and solving for x. So we have 0 equals 6x minus 5. Subtract 5 from both sides, then we have minus 6x equals minus 5. Divide both sides by minus 6 and we arrive to our final answer, x equals 5/6. So the x-intercept will be 5/6. We can confirm this by plugging in 5/6 into x for the original equation, and then getting y equals 5 minus 5, which equals 0. Another important skill to have in math is knowing how to represent equations on a graph. We already talked about it earlier, but let's do an example. Example 4. Graph the linear equation y equals 8x plus 9 on the coordinate plane. Graphing linear equations presented in this format is as easy as plugging in arbitrary x values, evaluating the y values, plotting the coordinate points, and drawing a line through them. As far as the slope, we will get to that soon. So, plugging in some convenient x values, we get these 3 coordinate points, 0, 9, minus 1, 1, and minus 2, minus 7. As you can see, we have plotted a few points that satisfy the linear equation and used them to graph the line. We didn't need to find the slope, but one important aspect of the slope is that it helps us navigate through different points on the line. The equation in slope-intercept form tells us that the slope is 8. We can then say that the slope is 8 over 1 since it is a ratio between changes in x and y values. The 8 tells us how far up or down to move along the y-axis to get to another y-coordinate on the line. The 1 tells us how far left or right to move along the x-axis to get to another x-coordinate on the line. This is also illustrated on the graph here. The slope-intercept form is a commonly used form for many equations you will come across in math and science. There are other forms that we will investigate, and they will serve their own purpose. Finally, it will be important to know how to rewrite these linear equations in their other forms. We will get to that later. See you in the next lesson. Algebra 1, Lesson 18, Point-Slope Form. The point-slope form is another alternative form used to represent the equation of a line. It is expressed in this form here. Y minus y1 equals m times x minus x1. Like with the slope-intercept form, the m represents the slope of the line, while x1 and y1 represent any coordinate point on that line. Let's do a quick example on how you would write an equation in point-slope form given some information about the line. Example 1. Write an equation in point-slope form that has a slope of 7 and goes through point 5, 9. Now, to write the equation, we simply substitute the values for m, x1, and y1. So, m equals 7, x1 equals 5, and y1 equals 9. When we plug those values in, we get our equation in point-slope form. Y minus 9 equals 7 times x minus 5. Let's do another example. Example 2. Write an equation in point-slope form of a line that has a slope of minus 3 and goes through point, minus 1, 6. Now with this example, we follow the same steps as the last example, except we need to be careful of which operation signs we use. In point-slope form, we would get y minus 6 equals minus 3 times x minus minus 1. The x minus minus 1 would need to be simplified to be x plus 1 to finalize your answer. In some problems, you are not given what the slope is for the line, but just 2 coordinate points. This shouldn't be an issue because we learned how to calculate the slope of a line given 2 points in a previous lesson. So solving those kinds of problems just takes a couple of extra steps. Example 3. Write an equation in point-slope form of a line that goes through points, minus 4 minus 5, and 8 minus 9. To solve this, we would need to refer back to the slope formula we used before. M equals y2 minus y1 over x2 minus x1. After plugging in the right points and doing some simplifying, we should get a slope of minus 1/3. Now the question is, which one of the 2 points do we use for the rest of the form? In this case, any point on the line would suffice, so either one of these equations below would be correct. In conclusion, the point-slope form is another form for an equation of a line that we could use when we know a point on the line and its slope. If we only know 2 points, we can find the slope using the slope formula and use one of the points to finish write the equation. Once again, by understanding the components of the equation and knowing how to manipulate it, we can easily find the equation of a line in the other different forms as well. In the next lesson, we will look at one more form called the standard form, and then we will look at how we can rewrite all the forms into each other. See you then. Algebra 1, Lesson 19, the standard form. Writing an equation in the standard form is a way of writing it in a specific, consistent format that allows for easy analysis and comparison with other equations. In general, the standard form of an equation is written in the form ax plus by equals c, where a, b, and c are constants, and x and y are variables. Let's break down what each of these components mean in more detail. 1. A and b are the coefficients of x and y, respectively. These values indicate the scale of the variables x and y in the equation. 2. C is a constant, which represents the solution or output of the equation. This means that when you plug in values for x and y that satisfy the equation, the output will always be equal to C. 3. X and y are the variables in the equation, which can take on any value as long as they satisfy the equation. So why is it useful to write equations in standard form? There are a few reasons. 1. Consistency. By writing equations in the same format, it's easier to compare and analyze them. You can quickly see how different equations are related to each other and identify patterns or similarities. 2. Easy plotting. When graphing equations, it's often helpful to write them in standard form first. This allows you to easily determine the intercepts, where the equation crosses the x and y axes, and plot the line. 3. Solving for variables. Some equations can be easier to solve for one variable if they're written in standard form. For example, if you want to solve for y in the equation ax plus by equals c, you can rearrange the equation to get y equals c minus ax over b. Let's look at some examples of equations written in standard form. Example 1. We have the equation 4x plus 6y equals 9. Find a, b, and c as it relates to the standard form of an equation. So, if we refer back to the standard form, we'll see that a equals 4, b equals 6, and c equals 9. Example 2. Using the previous example, 4x plus 6y equals 9. Find both the x-intercept and y-intercept. Let's get to it. One of the advantages of the standard form is that it is simple to find the x and y intercepts and just plot them on a graph and draw a line through them. You didn't even need to do any extra steps to find the slope, assuming you have a ruler and can draw straight lines, because in math we can't have crooked slopes. At least I don't think so. So, to find the y-intercept, we can just get rid of the 4x since we needed to plug in 0 anyway, and just solve the equation 6y equals 9. Divide both sides by 6 and then doing some simplifying, we get a y-intercept of 3/2. To find the x-intercept, we get rid of the term with the y and solve for x. So 4x equals 9. We divide by 4 on both sides and we get an x-intercept of 9/4. Example 3. Which one of these graphs represents the equation 4x plus 6y equals 9? If you chose C, that is correct. As you can see, the two intercepts we found also serve as points on the line. So, if we need to graph a line or even just find the slope, using the standard form is one of the easiest ways to get there. Example 4. Write the linear equation, minus 4x minus 7y equals 2 in slope-intercept form. To make sure we do the correct algebraic manipulation, we need to remember how the slope-intercept form is set up. So, to get the standard form to the slope-intercept form, we need to solve for y in terms of x. First, we add 4x to both sides. Then we divide both sides by minus 7. After doing those steps, we get the equation in slope-intercept form. Y equals minus 4 over 7x minus 2 over 7. Example 5. Write the following linear equation. Y equals 1/2 x plus 8 in the standard form. Now, there are a couple of conventional rules that we need to go over before we start the conversion to the standard form. 1. It's conventional for a to be the positive integer. Fractions and decimals should be excluded. If a is negative, you can multiply both sides of the equation by minus 1 to make it positive. 2. B and C can be positive or negative integers, but like with a, they should not be fractions or decimals. With that said, we can start the conversion process by subtracting 1/2 x from both sides. Now we have minus 1/2 x plus y equals 8. Since this is not in the conventional standard form, we need to multiply both sides of the equation by minus 2 to both get rid of the fraction as a and make it positive. Doing that, we get the final answer. X minus 2y equals minus 16. Example 6. Write the linear equation 5/6 x minus 10y equals minus 11 in point-slope form. This conversion is a little bit more of a challenge because we need to find the slope. There are a couple of ways to go about doing that. 1. You could find the x and y intercepts and calculate the slope from those two coordinate points. 2. You could convert into the slope-intercept form to easily find out what m equals. It's all up to what works for you and helps you figure out the slope the fastest. In my opinion, the fastest way to get to the slope is to convert into slope-intercept form. So we subtract minus 5/6 x from both sides. Then we divide both sides by minus 10. I'll give you a second to remember how to work with fractions. To find the slope, we need to divide the coefficient minus 5/6 by minus 10, which means multiplying by its reciprocal, which is minus 1/10. Now we have minus 5/6 times negative 1/10. Minus 5 times negative 1 is 5, and 6 times 10 is 60. Simplify and we find that our slope is 1/12. We aren't done yet though. We need to find the x1 and y1 coordinates. A quick way is to just use one of the x or y intercepts as a point, or you could plug in any random value of x in the slope-intercept form and solve for y to get an xy point that way. Let's say x equals 6, plug that into the equation, and we get y equals 1/12 times 6 plus 11 over 10, which equals 1/2 plus 11 over 10, which equals 32 over 20, which simplifies to 8/5. So a point we could use is 6/8 over 5. Now let's finish our problem. A linear equation in point-slope form for the same line. 5/6 x minus 10y equals minus 11 is y minus 8/5 equals 1/12 times x minus 6. So in the previous lessons, we went through the different forms we could write a linear equation in. In this lesson, we learned how to convert each form into one another, and learned that some forms of linear equations help us get to certain information quicker than others. Get some practice working with linear equations because, believe me, they aren't going anywhere. See you in the next lesson. Algebra 1, Lesson 20, Slopes of Parallel and Perpendicular Lines. In this lesson, we will go over the slopes of parallel and perpendicular lines. There are two basic rules when it comes to how the slopes of parallel and perpendicular lines interact. Parallel lines share the same slope, while perpendicular lines share a negative reciprocal slope. You can also verify by graphing the two equations on the coordinate plane. Here is a graph of the equations y equals 5x plus 2 and y equals 5x minus 6. As you can see, the lines have the same slope, and on the graph it shows that the two lines go on infinitely and will never cross, which is what parallel means. Here is a graph of the equations y equals 5/6 x plus 3 and y equals negative 6/5 x plus 5. As you can see, the slopes are negative reciprocals of each other, and on the graph it shows that the two lines are perpendicular to each other, which means they meet at a 90-degree angle. To clear up some possible confusion, when I say negative reciprocal, I mean to find the reciprocal and then negate it. For example, if the slope of a line is 13, then its reciprocal would be 1 over 13. Then if we negate it, we get negative 1 over 13, which makes it perpendicular to the line with a slope of 13. Make sure to remember that when you negate a number that is already negative, it turns into a positive number. Let's do a few examples to test what you've learned about the slopes of parallel and perpendicular lines. Example 1. Identify if the following lines are either parallel, perpendicular, or neither. Y equals 6x minus 1, and y equals minus 6x plus 7. So, you can tell by looking at the slopes that although the values for the slopes are similar, they are still not the exact same slope, so they are not parallel. The value of 6 was negated, but it wasn't turned into the reciprocal, so it is also not perpendicular, so the final answer is neither. Example 2. Identify if the following lines are either parallel, perpendicular, or neither. y1 equals 2/3 x minus 10, and y2 equals minus 3/2 x plus 3. So, we can identify the slopes of both these lines and can make a pretty good guess that they are perpendicular to each other. If we have any doubts, we could always apply this similar formula. For any line with a slope m, there can be a line with slope minus 1 over m that will be perpendicular to the original line. So if y1 has a slope of m equals 2/3, then the slope of a line perpendicular to y1, which is y2, must have a slope of minus 1 over 2/3. Applying our rules for dividing by fractions, we do in fact get minus 3/2 for the slope of I2, which confirms that the lines are perpendicular to each other. Sometimes you are given one equation and are asked to find another equation that goes through a certain point or points and is either parallel or perpendicular to the original line. These types of problems require some more work, but we'll break them down in a couple of examples. Example 3. Find the equation of a line that is parallel to the linear equation, y equals 7x minus 3, that also goes through point 1, 9. To solve this problem, we need to apply what we just recently learned in this lesson to what we learned a few lessons ago. In this lesson, we learned that parallel lines have the same slope, so we know the slope of the other line is 7. Next, we are given a point that the other line goes through, which is point 1, 9. Now we have a line with a slope of 7 that goes through 1, 9. This sounds like a familiar problem. If you remembered correctly, we solved problems like this in the point-slope form lesson. The point-slope form only requires the slope and one coordinate point, and we are given those, so all we have to do is use that form to create the equation for the parallel line, which is y minus 9 equals 7 times x minus 1. Now for the challenge problem. Insert evil laugh here. Example 4. Find the equation of a line, perpendicular to the linear equation, 2x plus 9y equals 3, that goes through points, minus 8, 3, and minus 6, 11. Write the corresponding line in slope-intercept form. This is the last lesson of this unit. You thought I wasn't going to go all out? Let's break this problem down in the next part. So, we have an equation of a line written in standard form, and we need to find another equation that is perpendicular and goes through a couple points, and then write it in slope-intercept form. Now that we know what the big picture is, we can start diving in. First things first, rest in peace, Uncle Phil. Okay, give me a break. These lessons take hours to script. Anyway, first we need to find the slope of the original line, which is not going to be as easy as the standard form, so we need to convert it into the slope-intercept form. Here are the steps. We subtract 2x from both sides, we get 9y equals minus 2x plus 3. Then we divide both sides by 9. Now we have y equals minus 2/9 x plus 1/3. So we know the slope of the original line is minus 2/9, which means that the slope of a line perpendicular to it must be 9/2. Now that we have the slope of the perpendicular line, we need to carefully think about our next steps. In the previous example, we found the slope of the other line and used the point to write the equation in point-slope form. The original problem is asking us to write an equation in slope-intercept form, meaning we must do more work, but let's pick point, minus 8, 3, and write our answer in point-slope form first. Our answer in point-slope form is y minus 3 equals 9/2 times x plus 8. Now our final step is to convert this into slope-intercept form. First, we distribute the 9/2 to the terms on the right side of the equation. We'll get y minus 3 equals 9/2 x plus 72 over 2 or 36. We need to isolate the y to finish the problem, so we add 3 to both sides. If we did our math right, the final answer should be y equals 9/2 x plus 39. Here is a graph of the two lines from the last example confirming that we did find the right equation. As you can see, the lines meet at a 90-degree angle, meaning that they are perpendicular to each other. And that's it for this lesson. If you could do that last problem, you should be able to do any problem from this unit in the knowledge checks, quizzes, and exams. As always, make sure you get the right amount of practice to build your confidence in understanding these concepts. If you feel a particular lesson or concept might have gone over your head, make sure to re-watch and pause at certain points to review the lecture notes and examples on the screen. With that said, see you in the next lesson. Algebra 1, Lesson 21, Linear Inequalities. Let's start talking about the concept of inequalities. An inequality is a mathematical statement that shows that one expression is greater or lesser than the other. Here are the important notations we need to know when solving inequalities. The less than sign means that the expression that comes before the sign is less than the expression that comes after it. The greater than sign means that the expression that comes before the sign is greater than the expression that comes after it. The less than or equal to sign means that the expression that comes before the sign is less than or equal to the expression that comes after it. The greater than or equal to sign means that the expression that comes before the sign is greater than or equal to the expression that comes after it. Inequalities are for the most part solved using the same rules we use to solve equations, with a few exceptions. We can understand inequalities by sketching them on a number line. Here are a few examples. Let's talk about how to solve linear inequalities. Solving linear inequalities is just like solving equations, except with a few more rules. The most obvious difference is that instead of using an equal sign, we use one of the inequality signs. For example, we would solve the inequality x plus 9 is less than 13, the same as the equation x plus 9 is equal to 13. Using addition and subtraction to solve inequalities is the same as using them to solve equations. So just pretend the inequality symbol is an equal sign, and it's business as usual. So the solution for the original inequality is x is less than 4. The sign doesn't change in this instance, but they do in other instances, and we'll get to those ones soon. Now, with addition and subtraction, the sign doesn't change, but they do in other instances, like with multiplication and division. That is because we can't keep the sign the same because of logical reasons. For example, 9 is greater than 6. If you multiply both sides by -4 and keep the sign the same, you'll get -4 times 9 is greater than -4 times 6, which you can evaluate as -36 is greater than -24. If you know anything about the number line, or just counting negative numbers in general, you'll know that this isn't true, and you will need to flip the sign the other way. So here are a couple of rules you need to know when trying to solve inequalities by multiplying and dividing. 1. You will not have to change the sign when multiplying or dividing each side of the inequality sign by a positive number. 2. You will have to change the sign when multiplying or dividing each side of the inequality sign by a negative number. Let's do a couple examples of solving linear inequalities. Example 1. Solve the linear inequality x minus 6 is greater than 10. This is one of those linear inequalities that you can solve like an equation. So, you easily add 6 to both sides of the inequality, and end up with x is greater than 16. Example 2. Solve the linear inequality -1/5 x plus 9 is less than 19. This is an inequality that will take 2 steps to solve. The first step is to subtract 9 from both sides. On the second step, we need to be careful. We need to multiply both sides by -5 to get the x by itself on the left side. Since we are multiplying both sides by a negative number, we need to remember to flip the sign in our final answer. With that said, the solution for this inequality is x is greater than -50. Linear inequalities could be used to solve a variety of real-world problems as well. We apply the same rules of setup that we learned in the algebraic word problems lesson. Let's get into a good example. A store sells bags of rice for $10 each, and bags of beans for $8 each. The store wants to make at least $400 in sales per day. Write a linear inequality that represents this situation, and find the minimum number of bags of rice and beans the store needs to sell to meet this goal. So, to tackle this problem, we need to get used to the idea that a lot of linear inequality word problems require a standard form setup. In this case, we have 2 variables we need to find: the minimum number of bags of rice and the minimum number of bags of beans. Our constant is the $400 minimum we need to make. So, our setup inequality is 10x plus 8y is greater than or equal to 400. Quick side note: when a word problem says, at least, you need to use the greater than or equal to symbol. If it says, at most, then use the lesser than or equal symbol. We have our setup inequality, 10x plus 8y is greater than or equal to 400. An easy way to solve this inequality is to split up the constant and solve for both x and y. So we split up the $400 into $200, and we write 2 new equations. 10x is greater than or equal to 200, and 8y is greater than or equal to 200. These are simple one-step equations, so you should already know what you need to do. Now, our solutions are x is greater than or equal to 20, and y is greater than or equal to 25. We aren't done yet, though. We need to answer what the word problem asked us. What is the minimum amount of rice and beans we need to sell to make at least $400? If we plug in those x and y solutions into our first setup inequality, we'll end up with $400 greater than or equal to $400, which is a logically true statement. We can now answer the word problem in plain English, or whatever language this could be translated to in the future. The minimum number of bags of rice we need to sell is 20, and the minimum number of bags of beans we need to sell is 25. Solving linear inequalities is very similar to solving linear equations. Some of them may take 1 step or may take multiple steps, but the rules of operations and balancing both sides stay the same. The only difference is knowing when to change the signs if there is multiplication or division on both sides by a negative number. In any case, If you find your final solution isn't logical when you test the inequality, then you'll probably need to flip the sign. See you in the next lesson. Algebra 1, Lesson 22, Combined Inequalities. Let's start talking about combined inequalities. Combined inequalities are inequalities that can be interpreted with the words and or. These are also called conjunctions, and disjunctions, respectively, are concepts taken from mathematical logic, which you will eventually study if you plan to have a career in mathematics or computer science. In this lesson, we will try to keep it simple. A conjunction inequality is only true when both inequalities are true. For example, the following inequality would read as x is greater than -3 and x is less than 6. A disjunction inequality is true when at least one of the inequalities is true. For example, x is less than 5 or x is greater than -3. Here are a few rules to remember about combined inequalities. 1. Solve each part of the inequality separately. 2. Always remember the basics of the inequality operators. The operators point to the lesser number and open up to the larger numbers. 3. Read the inequalities in their logic form or in plain English to get the intuition of what you are trying to solve. Let's do a couple of examples. Example 1. Solve the following inequality. So this inequality is a conjunction, so we read it as x plus 2 is less than 7 and greater than 1. Now we can solve each inequality separately and find x. First, let's do x plus 2 is less than 7. Subtract 2 from both sides. We end up with x is less than 5. Now, let's do x plus 2 is greater than 1. Subtract 2 from both sides. We end up with x is greater than -1. So our final solutions are x is less than 5 and x is greater than -1. Example 2. Find the solution for 3x plus 8 is greater than or equal to 7, or -2x minus 6 is less than -10. These are disjunction inequalities, so that means at least one of these must be true for us to have a solution. Let's solve them for x separately. Let's start with 3x plus 8 is greater than or equal to 7. Subtract 8 on both sides. We get 3x is greater than or equal to -1. Divide by 3 on both sides, and we get our first solution. X is greater than or equal to -1/3. Now let's do -2x minus 6 is less than -10. Add 6 on both sides. We get -2x is less than -4. Divide by -2 on both sides, flip the sign to greater than, and we get our second solution. X is greater than 2. So our solutions are x is greater than or equal to -1/3, or x is greater than 2. We can also represent combined inequalities on the number line. For greater than or less than inequalities, we use an open or empty circle and draw an arrow through all the points that satisfy the solution up to negative or positive infinity. For greater than or equal to or less than or equal to inequalities, we use a closed or filled-in circle and then draw the arrow. If the solutions are between 2 points on the line, then no arrows need to be drawn. Just connect the points by drawing a thick line between them. Here are a few examples of inequalities graphed on the number line. And that's it for our lesson on combined inequalities. Remember, not all combined inequalities will have 2 solutions. That's why it's a good idea to check to see if your solutions make logical sense. See you in the next lesson. Algebra 1, Lesson 23, Absolute Value Inequalities. Just like with equations, you can also run into inequalities that contain the absolute value of an expression. Let's review what an absolute value of a number means and its special property. The absolute value of a number defines its distance from 0 on the number line, and the absolute value of a number is never negative. For example, the absolute value of the number -6 can be written with the -6 inside two vertical bars like this below, and then we would evaluate that expression to equal the number 6, like this. Solving inequalities with absolute value expressions follow the same rules as solving equations with absolute value expressions. Inequalities with absolute value expressions will usually have two solutions. Let's do some examples. Example 1. The absolute value of 2x minus 3 is less than 5. When solving absolute value inequalities, you must look at two cases: the value inside the absolute value bars being positive and the value being negative. First, we solve the inequality when the value is positive, meaning we just take the expression outside the absolute value bars and solve it at its face value. So we have 2x minus 3 is less than 5. Add 3 on both sides, divide by 2 on both sides, then we get x is less than 4. Now we have one of the solutions, but we still need to solve the negative case. To do this, we must negate the value inside of the absolute value bars. So instead of 2x minus 3, we'll have minus in parentheses, 2x minus 3. We can distribute the negative sign to simplify, leaving us with negative 2x plus 3. Now we can solve a second inequality. Negative 2x plus 3 is less than 5. Subtract 3 on both sides, divide by minus 2 on both sides, flip the inequality sign, then we get x is greater than negative 1. Now we have a combined inequality that we can write as x is less than 4, and x is greater than negative 1. In the next example, we'll solve an absolute value inequality using a different approach. Example 2. Solve the following absolute value inequality. The absolute value of 3x minus 1 is greater than or equal to 4. In this instance, instead of negating the value inside of the absolute value bars, we can infer that the value could either be 4 or minus 4, based on the definition of the absolute value. When the value inside the absolute value bars is positive 4, that means all the positive numbers greater than or equal to 4 are solutions, so we can extract and solve the inequality without changing the sign to find our first general solution. When the value inside the absolute value bars is negative 4, that means all the negative numbers less than or equal to minus 4 are also solutions. This is because when you evaluate them, they become positive numbers greater than or equal to 4. In this case, we'll have to flip the sign and solve for minus 4 to get our other general solution. Okay, now let's solve the inequalities. First, we have 3x minus 1 is greater than or equal to 4. Add 1 to both sides, divide by 3 on both sides. Our first solution will be x is greater than or equal to 5/3. Let's do the other inequality. We have 3x minus 1 is less than or equal to negative 4. Add 1 to both sides, divide by 3 on both sides. Our last solution will be x is less than or equal to negative 1. Altogether, we have another combined inequality. This time we have disjunction inequalities. So our solutions are x is greater than or equal to 5/3 or x is less than or equal to negative 1. This concludes our lesson on absolute value inequalities. These problems may seem complicated, especially with the sign flips, but we are just combining all our knowledge about absolute value equations and inequalities and putting it to the test. Always remember the golden rule to check your solutions to see if they make logical sense. If you get a solution like x is less than 5 and x is greater than 5, then you know you made a mistake somewhere because that logically doesn't make any sense, so you would need to go back and check your work. Keep practicing. See you in the next lesson. Algebra 1, Lesson 24, Graphing Linear Inequalities. Just like we can graph linear equations on the coordinate plane, we can also graph linear inequalities on it as well. To graph a linear inequality, you need to follow these steps. 1. First, draw the graph of the line. The graph of the line will divide the coordinate plane into two half-planes. 2. If the inequality contains a less than or equal to, or greater than or equal to sign, the line will be solid, meaning all the points on the line are part of the solution. 3. If the inequality contains less than or greater than, the line will be dashed, meaning all the points on the line are not part of the solution. 4. To determine which side of the line to shade, it is easy to substitute a point into the inequality. 5. Make sure that y is on the left of the inequality sign. That way you will know the y-intercept and the slope to make it easy to graph the line. 6. Draw a solid or dashed line based on the criteria in steps 2 and 3. 7. Shade the appropriate region. Often it is easy to substitute the origin, 0, 0, into the inequality. Let's do some examples. Example 1. Graph the linear inequality y is less than 3x plus 2. Pause the video and try the problem out. The solution will be on the next part. The graph should look like this. Note: the right side of the graph is shaded, meaning that all points on that side validate the inequality. We'll pick a random point as an example. Let's pick the point 2 minus 3. Substituting the x and y points into the original inequality we get, minus 3 is less than 3 times 2 plus 2, which evaluates to minus 3 is less than 8, which is a true statement, which shows that we shaded the correct region. On the other hand, if we pick a point on the non-shaded side, like say, minus 4, 2, substitute the x and y values into the original, and evaluate, we'll get 2 is less than minus 10, which is not true, so we also confirmed the region that point is in should not be shaded. Let's do another example. Example 2. Graph the linear inequality y is greater than or equal to 4x plus 7. Pause the video and try the problem out. The solution will be in the next part. The graph should look like this, with a solid line drawn through the x and y intercepts and the left side shaded. Let me also ask this question though. Is the point, negative 7/4, 0, a solution? Without checking the points with substitution, you can see that because the point, negative 7/4, 0, is on a solid line, it is included in the solution. If you're too lazy to do work to figure out which region should be shaded, you can just intuitively remember that less than means that the shaded region is below the line, and that greater than means that the shaded region is above the line. It's easier to see it when the graph is a line with zero slope, like with these two examples. This concludes our lesson on graphing linear inequalities. Most of the work in this lesson is just a review of graphing linear equations, just with those important properties that are mandatory to have when graphing linear inequalities. If you need to, you can review the lessons on solving linear equations and graphs of linear equations. For now, let's close this unit and move forward to the last one for this course. See you there. Algebra 1, Lesson 25, Solving Systems of Equations by Graphing. Now it's time to double up. We are going to start looking into what we call systems of linear equations. A system of linear equations are simply two or more linear equations listed together. Like with single linear equations, there are various ways we can solve and analyze the solutions of a system of them. Graphing is one of the first ways we will look at systems of linear equations. We already know that the graph of a linear equation is a line, so when dealing with a system of linear equations, we need to graph two or more lines. The solutions or solution set of a system of linear equations is at the point where the lines intersect. This means that the solution is a coordinate point, or what we can call an ordered pair. Here's an example of a system of linear equations. We can represent them algebraically and on the graph. As stated previously, the solution set is the point of intersection, which is plotted on the graph. To solve a system of linear equations using the graphing method, follow these steps. 1. Put all of the equations in slope-intercept form when necessary. 2. Graph all the equations on the coordinate plane. 3. The point of intersection of the lines is the solution set, which again will be an ordered pair. 4. You can check your answers by plugging in the values from the ordered pair back into the system of linear equations. Let's do an example. Example 1. Rewrite both of the following equations in this system in slope-intercept form. First, we need to recognize that these equations are written in standard form, and we already learned how to rewrite them into slope-intercept form. Let's start with the first equation. 2x minus 5y equals 4. To put the equation in slope-intercept form, we need to isolate the y on the left side, doing a few basic algebra operations. So we subtract both sides by 2x, then we divide both sides by minus 5, hopefully remembering how to operate with fractions. Now we have our first equation in slope-intercept form, y equals 2/5 x minus 4/5. The second equation is more of the same work. I'll just put down the steps right here. So we'll get our second equation in slope-intercept as y equals 3/10 x minus 3/5. Now that we have our system of equations in slope-intercept form, we do some work to find the x and y intercepts. Pause the video and do the work, and the graph will be in the next part. If you need to review, revisit Unit 3. Your graph should look like this below. If it doesn't, then go back and check all your signs and fraction work. As you can see, they intersect at 2, 0. So that means that 2, 0 is the solution for this system of linear equations. In most cases, a system of linear equations will have one solution. In other cases, a system will be said to have no solution, or infinitely many solutions. When a system of equations has no solution, it means that the two equations are parallel to each other, meaning they never meet, also meaning they don't have any solution. So on a test problem, you would write no solution. When a system of equations has infinitely many solutions, it means that the equations are of lines that overlap and have the same slope. So on a test problem, if you see this, you would write infinitely many solutions. Here are systems of equations that have no solution and infinitely many solutions, represented both algebraically and on a graph. This concludes our lesson on systems of linear equations by graphing. In the next few lessons, we'll look at more computational ways to find the solutions of systems of equations. When it's all said and done, it's all up to you to decide which method is best for which type of system you are trying to solve. See you in the next lesson. Algebra 1, Lesson 26, Solving Systems of Equations by Substitution. Another way of finding the solution sets for systems of linear equations is to use the substitution method. The substitution method, like its namesake implies, involves substituting expressions to make solving for each unknown variable easier to do. Here are the steps you need to take to use the substitution method properly. 1. Solve one of the equations for either x or y. 2. Substitute the expression in the other equation and solve it. You will get the solution of one of the variables. 3. Take this solution and substitute it into either one of the original equations to get the value of the second variable. 4. Check the values for x and y by substituting them into the original equations. If that last part was somewhat confusing for you, let's do some examples. Example 1. Find the solution for the following system of equations. 7x plus 9y equals 4 and x equals 1. This is a softball problem, because you already have an x value that you can substitute and plug into the first equation in the system. So, let's just do that. Plug 1 into the x in the first equation, subtract 7 from both sides. Now we can solve for y by dividing by 9 on both sides. We get our solution set to be x equals 1 and y equals negative 1/3, or 1 negative 1/3. Now let's do a problem that involves a little bit more work. Example 2. Find the solution for the following system of equations. 3x minus 5y equals 2 and 6x minus 7y equals 9. Now things aren't so sweet, huh? Since we don't have any of the variables explicitly stated in the system of equations, we must do algebra to get to our solution set. This is lesson 26. Why did you think I was teaching you all that stuff before? First, we need to pick a variable to isolate on one side of either equation. Let's isolate the y in the second equation. Subtract the 6x on both sides and divide by -7 on both sides after that. Then we have y equals 6/7 x minus 9/7. So, now we must deal with fractions. Yes, we do, but first we need to make a substitution. Usually when we plug into a variable, we plug in a number. Well, it's time you learn that we can plug in whole expressions into variables as well. We solved the y in the second equation to get an expression instead of a number like we usually do. But the same rules apply when plugging that expression into the other y in the same system of equations. So, we'll substitute 6/7 x minus 9/7 for the y in the first equation. Doing that we'll get 3x minus 5 times 6/7 x minus 9/7 equals 2. Let's unravel this equation in the next part. We must simplify the left side of the equation and solve for x. Remember the distributive property? Can you do them with fractions? Well, if you can't, you should review some previous lessons, but for now let's work through this. The -5 outside the parentheses must be multiplied by the numerators of the fractions inside. So we'll get -37 x plus 45/7. Note the sign change. We distributed the -5 instead of 5 because of the subtraction sign in front of it. That's a common mistake that could cause you to do a whole lot of work and come up with the wrong answer, like I just did before, during production of this lesson. Now we can write the first equation like this. 3x minus -37, x plus 45/7 equals 2. Next, we combine like terms. Subtract 45/7 from both sides. After that, we must do what is probably some of you guys' worst nightmare, adding fractions with different denominators. I feel like you could use the practice, so you can pause now, and we'll continue in the next part. We have like terms on both sides, and now we need to add fractions to simplify them. Here's the groundwork. Check to see if you took the same or similar steps. After all that chaos, we can finally solve for x by multiplying both sides by -7/9. And we get x equals -31/7 times -7/9 equals 31/9. But hold on, we aren't done yet though. We must substitute that x value into the second equation that we solved before in terms of y. So quickly we evaluate it like this below. So after all that work, we finally end up with our solution set, 31/9 5/3. In conclusion, I'm tired. It's easier to just graph these problems and approximate. But hey, we still have one more method we can use to solve these systems of equations. See you in the next lesson. Algebra 1, Lesson 27, Solving Systems of Equations by Elimination. Another additional way of finding the solution sets for systems of linear equations is to use the elimination method. The elimination method helps you add and subtract equations to get a new equation with only one unknown variable. It is best to use the elimination method when two of the equations have the same or opposite coefficients for one of the terms. As usual, there are some steps we must follow to use the elimination method effectively. 1. Make sure the variables are on one side and the constant on the other, with the like terms lined up. 2. If necessary, find a common multiple of the like terms. For example, if 3x and 2x are in the system, multiply the equations by 2 and -3, so that 6x and -6x will appear in the system and can be eliminated first. 3. Add or subtract the equations to complete the elimination. 4. Solve the equation. 5. Use that value that you just found and plug it into one of the equations in the system, so you can solve for the other variable. Let's give an example. Example 1. Solve the system of equations using elimination. Looking at this system, it is formatted in a way where you can combine like terms vertically. We will need to do this to eliminate either the x or y variables from the system, so we can solve for the other one. Let's pick y to eliminate first. So what we do is look for a common multiple of the coefficients attached to y, and scale the equations up in a way where the y-like terms cancel out, and leaves us with just the x-like terms. In this example, we'll use the number 15. If we scale up the first equation by 5, meaning multiplying both sides by 5, we'll get 10x plus 15y equals 35. If we scale up the second equation by 3, meaning multiplying both sides by 3, we'll get 12x minus 15y equals 3. So now we get a new system right here. With the new system of equations, which is really the original system but just scaled up, we can eliminate the y values by vertically combining both equations. Note, scaling up equations doesn't change the value of the unknown variables, just like scaling up fractions doesn't change their true value. So, when we eliminate the y from the system, we add the other like terms together and solve for x. These are the steps below. So our x solution is x equals 38 over 22 or 19 over 11. Now to find our y solution. To find that out, we simply plug in the x value we just found into either of the equations and then solve for y. Let's pick the first equation and do the steps. We plug in 19 over 11 into x, evaluate it to be 38 over 11, subtract 38 over 11 from both sides. Finally, divide by 3 on both sides. After evaluating the fractions on the right side, we'll get a y value of 13 over 11. That leaves us with our final solution set for this system of equations, which is 19 over 11, 13 over 11. In conclusion, if you can do the example in this lesson, then you should be able to solve any system of equations using the elimination method. There will be knowledge checks and practice questions available for you as well. The important thing to remember is that you need to scale the equations in a way where if you combine the like terms vertically, then you eliminate one of the variables. This clears you up to solve for the other one. Once the other variable is solved, you simply pick one of the equations and plug that value in. This will leave you to solve for the original variable that you eliminated first. Combine those like terms vertically, then you can solve for that variable, and you'll have both the x and y parts for your solution. If you are unsure of your solution, or think you've made a mistake in your calculations, you can always substitute those x and y values back into the system and see if the equations are still valid, whether it's by graphing, substitution, or elimination. Your method of solving systems of equations will be all up to your preference, or what is more convenient based on how the system is set up. Now that we've gotten the methods down, let's do some word problems. Evil laugh. See you victims in the next lesson. Algebra 1, Lesson 28, Solving Word Problems with Systems of Equations. We have solved simple algebraic word problems back in Lesson 14. Now we are about to use those skills to solve word problems that require setting up systems of equations. Here are some tips on how to deal with solving word problems with systems of equations. 1. Read the problem carefully to identify the unknown variables and the relationships between them. Write down any equations that represent the information given in the problem. 2. Let x and y be the unknown variables, and write down two equations in the form of a, x plus b, y equals c, to represent the problem. 3. Solve the system of equations by using one of the methods, such as elimination or substitution. 4. Check the solution by substituting the values found for the variables back into the original equations, and verifying that they are true. Example 1. A movie theater sells two types of tickets. Adult tickets cost $18 each, and child tickets cost $14 each. On a particular day, the theater sold a total of 180 tickets and earned $2,640 in revenue. How many of each type of ticket were sold? So, let's start. First, we need to let x be the number of adult tickets sold and y be the number of child tickets sold. We can write two equations based on the information given in the problem. First equation is x plus y equals 180. This equation represents the number of tickets sold for both children and adults added up together to equal 180 tickets. The second equation is 18x plus 14y equals 2640. This equation represents the cost of each type of ticket sold added up to equal the total amount of money made from sales. Now that we have our two equations to represent our system of equations, we can go ahead and start solving it. In the last lesson, I mentioned that you could use any method to solve a system of equations. In this situation, I believe the substitution method would suffice. Let's start by solving for y in terms of x in the first equation. We do that by subtracting x from both sides. Then we substitute the expression in terms of y into the second equation. Evaluate and simplify. Now we can solve for x by dividing both sides by 4. We'll find that x equals 30. Plugging that back into the first equation and solving for y, we'll get 30 plus y equals 180. So, y would equal 150. Now that we know the values of x and y, we can finally answer the word problem. The word problem asks us for how much of each type of ticket was sold, which means our answers are the x and y solutions we just solved. So, in conclusion, the movie theater sold 30 adult tickets and 150 child tickets, equaling the 180 total tickets sold. That was just one example of a word problem being solved using a system of equations. As always with these word problems, reading comprehension and understanding what the problem is asking for is key. Translating what the problem is asking for into the right equations and checking solutions are the next important steps. A lot of these systems of equations word problems will follow the same process as the example we just did, so make sure you review it and review all your work to see if you're on the right track to do further practice problems. Good luck, and see you in the next lesson. Algebra 1, Lesson 29, Solving Systems of Linear Inequalities. Just like with linear equations, we can also have a system of linear inequalities. To find the solution set of a pair of linear inequalities, we must find the ordered pairs that satisfy both inequalities. To do this, we need to graph and shade the appropriate sides of each inequality. After we do that, we'll see that the region where both shaded areas overlap is the solution set. To help us graph a system of linear inequalities with accuracy, we need to follow these rules. 1. Like before, make sure that y is on the left of each inequality sign. That way you will know the y-intercept and the slope. 2. Sometimes you may have to find the x and y-intercepts and then graph each inequality. 3. Graph the first inequality and shade the appropriate area. 4. Graph the second inequality and shade the appropriate region. 5. When drawing the graphs, remember to draw a solid line if less than or equal to, and greater than or equal to signs are used. Draw a dashed line if less than and greater than signs are used. 6. The region where the two shaded areas overlap is the solution set. 7. Check your work by using a point from the overlapped area. Substitute it into each inequality and evaluate. They both need to read true statements. Let's work on an example. Example 1. Graph the following system of inequalities. Check to see if the point, -1, 5, is part of the solution set. Pause the video and work on this problem. We'll have the solution in the next part. Your graph should look something like this. Now look at the point, -1, 5. Think about this carefully. Is point, -1, 5, a solution for both equations? I'll give you a second. If you said yes, then you were wrong. The point, -1, 5, may be a solution for the second equation in the system, but it is not a solution for the first equation. So the point, -1, 5, is not part of the solution for the system of inequalities. Example 2. Which one of the following points are a part of the solution for the previous system of inequalities? A, -5, -1, B, 1, 4, C, 0, -4, D, 1, -3. If you chose D, then you are correct. A couple of the other points may be solutions for the equations individually, but mutually, they are not valid for both equations. To do a quick check, let's substitute the x and y values and evaluate to see if we end up with true statements. So, as we just worked it out, we ended up with true statements when we evaluated the system of inequalities with a point from their solution set. If we wanted a more algebraic way to write the solution set to be all-inclusive, we would look at the intersection of both lines and see that the shaded area represents all x values greater than 1/3, and all the corresponding y values are less than or equal to -1. You could also solve the system like we do with equations, with the substitution and elimination methods, but I feel it's easier to graph so you won't get caught up with mistakes like forgetting to flip the signs and such. In conclusion, solving systems of linear inequalities need to be done carefully because of all the different technicalities with the true solution sets. The substitution and elimination methods could be used to solve them as well, but graphing them lets you see the whole picture more clearly, in my opinion. In any case, use what method that is practical and that you're comfortable with. Algebra 1, Lesson 30. Solving word problems with systems of linear inequalities. When dealing with real-world problems, we often encounter situations where we need to make decisions within certain limits or constraints. For example, if you have a limited amount of time and money, you might need to decide how much of each resource you can use. In these cases, systems of linear inequalities can help model these constraints, allowing us to find feasible solutions. These are the usual steps you'll need to take to solve word problems with systems of linear inequalities. 1. Understand the problem. Read the problem carefully to identify what quantities the variables will represent. 2. Define the variables. Assign variables, such as x and y, to represent the unknown quantities. 3. Write the inequalities. Based on the problem's constraints, write down inequalities that represent these limits. 4. Graph the system of inequalities. Plot each inequality on a graph to find the solution region that satisfies all inequalities. 5. Interpret the solution. Analyze the feasible region, where all inequalities overlap, and check if it answers the problem's question. Example 1. Emma is planning a fundraiser where she will sell baked goods, cookies and brownies. Each cookie takes 2 minutes to make, and each brownie takes 3 minutes. She has a maximum of 5 hours, 300 minutes, available for baking. Additionally, she wants to make at least 50 items in total, but no more than 100. Write a system of inequalities to represent this situation and find the feasible solution set. Let's get started. First, we need to define the variables we will be using in the system. We can let x be the number of cookies Emma bakes, and let y be the number of brownies Emma bakes. Next, we'll need to identify the constraints. We know that each cookie takes 2 minutes, and each brownie takes 3 minutes, and she has a maximum of 300 minutes. This translates to the inequality 2x plus 3y is less than or equal to 300. Now we need to write inequalities for the total items constraint. Emma wants to make at least 50 items but no more than 100. We can write 2 inequalities that represent the constraint. X plus y is greater than or equal to 50, and x plus y is less than or equal to 100. Now let's put all the inequalities together and go from there. Here we have the 3 inequalities we just figured out. Now we must figure out the best way to solve this system of inequalities. If you remember from the last lesson, my preference is to graph systems of linear inequalities and figure out the shaded region that contains all the real solutions. So let's do that right now with this system. Pause now and try to figure out the graph yourselves. The correct graph will be on the next part. Your graph should look something like this. The solution set is the region that is the darkest shaded. For more clarification or help, if you had trouble making the graph, here are the 3 inequalities listed with their x and y intercepts. To finish the problem, here is how we interpret the solution. The darkest shaded overlapping area on the graph shows the feasible values of x and y, meaning the combinations of cookies and brownies Emma can bake within her time limit and quantity requirements. Any point in the overlapping region is a possible solution, such as the coordinate point, 40, 60, meaning 40 cookies and 60 brownies. In this lesson, we learned how to translate word problems with constraints into systems of linear inequalities. By defining variables, writing inequalities, and graphing them, we can find a feasible solution region that meets all the problem's conditions. Practicing with these kinds of problems will help you understand how systems of inequalities can be applied in real-world situations, from budgeting to planning and optimizing resources.